So we're going to look at a reaction where we have some apple pulp that we want to ferment. So this is something you could encounter as a source of carbohydrates in biotech. And we are being told that the pulp that we're using, 30% of it is dry matter, 70% is water. And that dry matter is made up of 81% carbohydrates, 19% inerts, so stuff that doesn't react. And then, actually, can I make this a bit larger? Let's just try. There we go. And we're being told this is the reaction we expect to happen. So the carbohydrates and some water turns into some product and CO2. Okay, so there'll be some microorganisms that'll do this conversion. And then the question is, what is the excess of water and what would it look like if I added 20 kilograms of apple pulp? So we're going to take that information. Actually, let's just take that part. Where is my snipper tool? We're going to grab this part. Actually, let's do that part. Jump over to Excel. I've already set up part of it. And let's have a look at what we can do here. So I'll do what I always do. Select or create my streams, apples and my product stream, or feed and product, and then percentages of all the different components that I know of. And we'll just start to fill it out. For the apples, I know it's 70% water. Carbohydrates is a bit tricky because it's not 81% carbohydrates. It's 81% of the dry matter, which in itself is 30% of the total weight. The easiest way for me to enter that into Excel is that I, instead of typing in the values, I say, okay, it's 30% times 81%. So 24.3% in this case. Same for the inerts. I take 30% times the 19%, which are the inerts, and I have that. The rest of these are 0. Nothing enters from those. And I still have the water. Good. For my exiting, well, I don't know. Let's start out by saying I don't know what these are. The total I know because I've already forgotten. 20 kilograms. We are going to use 20 kilograms as the basis, and we don't know how much is going to exit. In theory, we could say already, I know that 20 kilograms are going to exit because it's one stream in, one stream out. But whatever. Calculating the amounts we have, total times the percentage, fill it to the right, fill it down. So now I have a way of calculating the mass of carbohydrates, inerts, and so on. Okay? And all of these I'm going to say I don't know what they are right now. So the first question is, which one is the limiting reagent? We were already told that it's going to be the water. And we can actually see because they react 1 to 1. And oh, we actually have to convert it into moles first. Oh dear Lord. We'll do that down here. Dum, dum, dum. So that is a common trap. I can't look at the masses. I have to look at how many moles of each component I have. We're just going to take the heading that we're using there. Going to put it there. We're going to take these two and move them down one. And up here, I'm just going to write molar masses for the different components because I need them for my calculations. Now we're going to be lazy and cheat and say, okay, water H2O, 2 plus 16, close enough. The carbohydrates, 12 carbons, 22 hydrogens, and 11 oxygens. The inerts I don't really care about. And over here I have, 2 carbons, 6 hydrogens, and an oxygen. 12 plus 2 times 16. So I'm just using the approximate masses. Carbon is 12, oxygen is 16, hydrogen is 1. That'll work fine for now. So if I want to calculate the moles of water, I will simply take, I need to do this right, where do we have it? Is that right? Yeah. So I'm going to take the mass and I'm going to divide it by my molar mass. And I just have to be careful here because like that. Oh no. Oh, can't I do this easily? Let's see, when I move it to the right, I want that, yeah, like that. We're just gonna check if this works. No, what went wrong? Oh, it's because we don't have any value there. Let's just give it 1. Doesn't matter. The inerts we don't really have to deal with, but we'll just keep them anyways. So now I have a way of calculating the number of moles. If I wanted to, I could calculate the totals. We don't really need them. Hang on, this doesn't seem right, does it? Yeah. So if I look at the moles, I have 0.77 moles of water and 0.01 of carbohydrates. So that means if we look here, they react 1 to 1. I have a vast excess of water. Some of you might say, oh, hang on, Thomas, you're messing up the units. Yeah, this is gonna be, that must be kilomoles and not moles, but it's fine, it'll work. Numerically, it won't matter. So in terms of excess, well, I would just take the amount I have compared to the amount I need. So I already know that I have an excess of water of 54. If I want to convert that into percentages, 5,473%. I basically have 54, almost 55 times as much water as I need. Okay? If I wanted to calculate what comes out, we would have to assume some form of conversion. If we assume that my carbohydrates, all of that is converted, that means that the percentage of carbohydrates must be 0, no longer an unknown. I can take one of my percentages here and say it's 1 minus the sum of all the other percentages. There we go. And that should be fine. So this one is also no longer an unknown. And then we start to set up our atomic balances. So again, I'm going to take my components. I'm going to paste them transposed. Can you actually do it easily? No. Paste special, transpose, there we go. I have carbon, I have hydrogen, I have oxygen, and we just have to fill out for each of them. The water, 2 hydrogen, 1 oxygen. What was the carbohydrates? 12 carbon, 22, 11. Inerts, don't care. For my product here, 2 carbon, 6 hydrogen and 1 oxygen. CO2, like that. And then again over here I can calculate my carbon, hydrogen and oxygen, and I do it the exact same way as I did before. I want this, not the sum product of these and the transpose of these and all of that, and write them down. And then I can set up my balances, carbon in minus carbon out, hydrogen in, hydrogen out, oxygen in, oxygen out, and that should be enough to solve this. You could say, well, hang on, we need another equation here. We need to somehow figure out what's going on. What we could do is we could throw in a total mass balance and say the entering minus the exiting have to be the same. So this is my mass, and then I have my atomic balances. At this point, I should be able to set up a solver. One of them has to be 0, so does the other 3. equal to 0. And finally, these are my variables. And please try and solve. Solver found a solution.